This is the second part of programming for food design based on Canadian Code of CSA O86 version 2019. In the current post, I have discussed design and programming on built-up beams, NLT, GLT, and CLT panels. Here is the summary of our current post. I will talk about the design flowchart for build-up beams, nail-laminated timber, glue-laminated timber, and cross-laminated timber. For each part, I have explained about the design flowcharts. Then we will study 3 examples and calculate each of these examples using 3 methods: wood design manual selection tables, hand calculation, and software calculations. Our references are Canadian Code of CSA O86 version 2019 and Wood Design Manual 2020. This is the definition of build-up beams based on CSA O86. Build-up beams consisting of 2 or more individual members of the same that are fastened or glued together so that the beam will deflect as a unit. This is the design flowchart for build-up beams as per CSA O86. This is very similar to design flowchart for sawn lumber joist. And the first step, we need to find the specified strengths such as FB, FV, and modulus of elasticity from table 6.4. In the next step, modification factors should be calculated based on the relevant tables or clauses. After that, the gross area, section modulus, and moment of inertia should be calculated. Then we calculate the allowable bending, shear, and flexural strength, FB, FV, and FF, by multiplying the specified strengths by the modification factors. In the final step, we calculate the factored bending and shear resistant, bending stiffness EI, and the fracture shear resistant at the notch. The main difference is applying numbers of plies to this formula. Example 1 is related to build-up beams. Calculate MRVR and ESI for single span floor build-up beam of 38 by 286 mm for the following conditions: standard load duration, dry service condition, untreated, fully lateral supported by subfloor, case 1 system, 2-ply and 3-ply. Use Douglas firm large. Select structural sawn lumber. Because of the similarity of this part with the design of sawn lumber choice, actually I didn't talk about the hand calculation and focus just on build-up beam selection tables and software calculation. In the selection tables in Wood Design Manual, we can easily find the species of selected structure, Douglas firm large, and the profile section of 38 by 286 very easily in 2-ply. MRVR ESI is 16.9, 27.3, and 1850. In the software calculation, we just select the check option, width of the section 38 and depth of the section 286, number of plies 2, a species combination Douglas firm large, and the grade categories SS, and the system factors case 1. After that, just press the build-up design check, and program will calculate the MRVR ESI. For the software calculation, actually I can select the design menu and then build-up beams. In the part of design and check, I can select the check. It's already checked. Width of the section is 38 and depth of the section should be 286. I can select the number of plies and the species combination. It's okay. And the grade categories is SS. It's okay. Case 1 is okay. And the final steps, I just press the build up design or check. Program calculate MRVR ESI. If I change it to 3 plies, the program also changes the design for the 3 plies, and also I can design it or check it for 4 plies or 5 plies. The next section is nail-laminated timber or NLT, which the lumber is connected by nail together. We have two options for grading, visually graded or MSR and MEL, machine stress rated MSR, and machine evaluated lumber. In the case of MSR and MEL, the size factor KZ should be taken as 1. In the section of 6.5.10 3.1, the connection requirements is explained. This is the design flowchart for NLT. First, we should find a specific strength for bending, shear, and so on based on the grade of the section. If it's a visually graded, we should use the table 6.4, or if it's the graded on MSR, we should use the table 6.8. In the next part, we should find the factors, load duration factor, service condition factor, and so on. I will explain later on the example. After that, we should find the area, S and I, section modulus, and moment of inertia. And after that, we should find FB, FV, and MR, VR, ESI. They are the simple formulation. The difference is to find the deflection, serviceability, and I will explain it in the example. Example 2 is related to NLT panel. Design a single span NLT roof panel for the following conditions. Panel span is 3.5 meter. Specified dead load is 1.5 kilopascal. Panel self weight included. Specified live load is equal to 3 kilopascal. Standard load duration, dry service condition, untraded. Use MSR 1650 FB 1.5E consisting of SPF lumber. The first calculation is based on the Wood Design Manual. The total factor load is equal to 1.5 multiplied by 1.5 plus 1.5 multiplied by 3 is equal to 6.38 kilopascal. WF is 6.38 multiplied by 1. The width of the panel is 6.38 kilonewton per meter. MF, our moment is WFL power 2 over 8 is 6.38 multiplied by 3.5 power 2 over 8 is equal to 9.77 kilonewton meter per meter. WF is equal to WF, VF is equal to WFL over 2, 6.38 multiplied by 3.5 over 2 is equal to 11.2 kilonewton. Then we should use the Wood Design Manual panel section tables. The width of the section is 38 millimeter, and we should use the NLT strength pages with the MSR grade and species of 1650 FB 1.5E. The thickness of panel is 89, therefore MR will be 31.2, which is greater than MF 9.77, and VR, the shear strength, is 150 kilonewton per meter, which is greater than 11.2 kilonewton per meter. And also ESI is 605 multiplied by 10 power 9 Newton millimeter square per over M. In the next step, we should check the maximum span of panel. In the Wood Design Manual panel selection tables, we should check their serviceability roof deflection part. Our dead load is 1.5 kilopascal and our snow load is 3 kilopascal. Also, our grade is MSR and the species is 1650 FB 1.5E. The panel thickness is 89 millimeters. Therefore, the maximum span of panel is 3.86 meter, which is greater than 3.5 meter, and it's acceptable. Therefore, we can use the section of 38 by 89 millimeter MSR, 1650 FB, 1.5 E SPF lumber. In the hand calculation method, first we should find the specified strengths FB and FV for bending and shear. We have the MSR lumber, therefore we should use the table 6.8, and our grade is 1650 FB, 1.5 E, therefore bending specified strength FB is 23.9 and the modulus of elasticity is 10,300 megapascal. In the next step, we should find the K factors. The load duration factor is equal 1 because it's a standard load duration. The K for service condition factor is 1 also because we have the dry service condition. Also, the treatment factor KT is 1 because we have untreated system. And the KZB and KZV for the size factor is also 1 because we have grade MSR. We have also the case 1 there for KH is 1.1, the system factor. And KL, the lateral stability factor, is 1 for all panels. In the next step, we can find the A area of the section. BD is equal to BD. B is the width of the panel, is 1000 millimeter or 1 meter, multiplied by the depth of the section is 89. Therefore, the AG is 89,000 square millimeter. S is BD power 2 over 6, and I is BD power 3 over 12. We can calculate it easily. And also, we can find the FB and FV just by putting the amount of the values and K factors on the formula. Now we have all the parameters we need, and just we put the formula and find the MR, VR, and ESI as 31.2 megapascal for moment, 149.8 megapascal for shear, and ESI is equal to 605.1 megapascal. In the last step, we should find the maximum span based on the serviceability. We have the roof panel, so we should use the right part of the formula for the roof panels. We have WDLEAESI, therefore we can put the parameters on the formula and find the maximum span as 3.86 meter. In the third method, we can use the software calculation after run the program. We can select the design menu, and after that we can select the nail-laminated timber panels option. Then we can check the design option here because we want to design the panel. And it is a roof panel, so we check the roof panel. We enter the panel span 3.5. We define the specified dead load, live load, and our species combination is SPF. Also, the grade categories is MSR, 1650 FB, 1.5 E. Case 1 is okay. And then we can press the NLT design check, program calculate everything, and show the result here. This section is glue-laminated timber. GLT is very similar to NLT, nail-laminated timber. Instead of nail, we use the glue to stick the lamination timbers together. This is the design flowchart for GLT. Glue-laminated timber panels is very similar to NLT, so I don't want to explain it again. The last section of this post is CLT or cross-laminated timber. Based on the wood design manual definition, CLT panels consist of several layers of lumber laid flatwise and glued together on their wide faces. Panels typically consist of 3 to 9 alternating layers. Based on the clause 8.2, the CLT layout shall be a balanced combination of orthogonal layers where all laminations oriented in the same direction are made of sound lumber of the same grade and species combinations. The primary CLT grades are E1, E2, E3, V1, and V2 based on the definition on table 8.1. This is the design flowchart for CLT. First, we should define B0, the width of the panel, number of plays, a span grade, TI, ZI, WF. Then we should find the specific strength FB, FS, and so on based on table 8.2. Then we should define the low duration factors, service condition factors, and so on. In the next step, we should calculate the E effective, G effective, and S effective section of modulus in two directions. In the next step, we should define FB and FV, which is equal to FS. Then we can calculate the moment and shear in two directions. Also, we should check the deflection for serviceability in two directions. The parameter of B0 span grade, TI and WF are given data. The number of plies can be 3, 5, 7, or 9. We should calculate ZI, which is the geometric center of each layer to the natural axis in two directions. In the next step, we should find the specific strength in two direction longitudinal layers and transverse layers, and find FBE and FS. The low duration factor KD can be calculated based on the formula of KD is equal 1. Subtract 0.5 log PL over PS should be greater or equal to 0.65. PL is specified as a specified long-term load, and PS is equal to specified standard term load based on snow and live load. The service condition factor Ks is equal for KSB, KSV, and KSF. For all K, it's equal to 1. The treatment factor KT, system factor KH, and the lateral stability factor KL is equal to 1. In the next step, we should calculate the modulus of elasticity of lamination in two directions, also the shear modulus of laminations in two directions. There are the formula to calculation the E effective and G effective in two directionals. This is the whole part of design flowchart for cross-laminated timber panel CLT. In the final step, we should check deflection and vibration of CLT panels in major and minor strength directions of the panel. In calculation of deflection of CLT panels, delta max is equal to delta ST short term plus delta LT long term multiplied by K creep, which is 2 for dry service condition. In the vibration performance of CLT floors, LV, the vibration control span limit, or the maximum span in meter, must be smaller than or equal 0.11 multiplied by E effective over 10 power 6 whole power 0.29 divided by M power 0.12, which M is a linear mass of CLT for a 1 meter wide panel based on kilogram over meter. This is the whole part of design flowchart for cross-laminated timber panel CLT. Example 3 is related to design of a CLT panel. Design single span floor CLT panels for the following conditions. Panel span equals 6 meter, panel width equals 1 meter, specified dead load equals 1.5 kilopascal, the self-load included. A specified live load equals 2.4 kilopascal. A standard load duration, dry service condition, and untreated. Use stress grade V1 oriented in its major strength direction. The thickness of each ply is 35 millimeter. The first calculation is based on wood design manual. The total factor load equals 1.25 multiplied by 1.5 plus 1.5 multiplied by 2.4 equals 5.48 kilopascal. WF is equal 5.48 multiplied by 1 is equal 5.48 kilonewton per meter. The moment MF is equal WF L power 2 over 8, 5.48 multiplied by 6 power 2 over 8 equals 24.6 kilonewton meter over meter. WF shear is equal WFL over 2 equals 5.48 multiplied by 6 over 2 equals 16.4 kilonewton meter. Therefore, in design wood manual, the plies with the thickness of 35, the grade with V1, we should find the major moment must be greater than 24.6, which is the 31.2 is greater than 24.6, and the shear of 66.2, which is greater than 60.4. In the next step, we should check the floor vibration maximum span, which for the grade V1 with number of 5 layers, we will have 5.27 meter in major strength direction, which is smaller than 6 meter. For the deflection check of CLT, we should find the related table. The dead plus LS for our problem is 1.5 kilopascal, and the live load is 2.4 in the major direction. Our grade is V1, a number of plays is 5. Therefore, the maximum span length is 6.65 meter, which is greater than 6 meter, so it's acceptable in this direction. Therefore, for serviceability, the floor vibration with a maximum span of 5.27 meters is not acceptable. Therefore, we can increase the number of plies to 7, or we can change the grade of the CLT. In the second method, we can use the hand calculation to design the CLT panels for this example. First, we should define the basic parameters like B0, which is equals to 1 meter, span equals 6 meter, TI is equal 35 millimeter for all layers. And the next step, we should calculate the Z1 to Z5. Z1 is the geometry center of the first layer to the natural axis. We have a 35 over 2 here, a 35 millimeter here, and a 35 over 2 millimeters. Therefore, the Z1 will be equal to 70 millimeters. Z2 is the distance of the second layer, the center of geometry of the second layer to the natural axis. We have a 35 over 2 here and a 35 over 2 here. Therefore, we will have a 35 for the Z2. Z3 is 0, and Z4 and Z5 are equal Z2 and ZY respectively, but in the negative direction of Y. In the next step, we can specify the strength and modulus of elasticity for layers based on table 8.2. Therefore, we have the stress grade of V1 for the longitudinal layers. FB is 10 megapascal, E is 11,000, and in transverse layer, FB is 4.6 and E is 10,000 megapascal. FS is equal to 0.63 megapascal for the longitudinal and transverse directions. In the next step, we want to find the K factors. In our example, our factors are equal 1. The elastic modulus and shear modulus in the main direction and direction with 90 degree will be calculated based on the formulation as we shown here. E effective 0 is equal to 3921, E effective 19 is equal to 930, G effective 0 is 16, and G effective 19 is 70.3 multiplied by 10 power 6 Newton square millimeter per meter. The effective section of modulus in two directions will be calculated based these formulations. SE effective 0 is equal 4074, and S effective 90 is equal 1771.94 multiplied by 10 power 3 Newton square millimeter per meter. Also, the effective moment in two directions will be calculated based on the formulation, and shear for two directions also will be calculated. And the right side, we can see the amount of the moment and shear in two directions. The deflection and vibration of floor for major and minor resting direction will be calculated with this formulation, and therefore we will have the maximum span for the major direction will be 6.65. Maximum span mirror direction will be 4.14, and maximum span for vibration in major direction 5.27, and in minor direction will be 3.45 meter. The last method we want to use the software calculation. Therefore, after running the program, I select the design menu and select cross-laminated timber CLT. In the related form, I will enter the thickness of the layers. They are all plies are the same thickness, 35, and this is check and floor. Floor panel, and the panel span is 6 meter. The dead load and live load, specified dead and live load is correct, and the grade categories will be V1. Everything is there. Okay, so in the next step, I click CLT design check, and program will give me all results here.